probability or that expected behavior is good, and so on and so forth. And so inevitably, any discussion of randomization turns to a discussion of probability and tricks to analyze algorithms using certain tricks. So we're going to talk about these tricks today. Okay? So it's going to be a lot of probability theory, a lot of stuff like random variables and things like that. That's all very important because that's how we think about randomization. We think in terms of these things. All right. So before we even get to tailbones, and I'll explain what they are in a minute, I want to talk about something even more basic. Right? So we've seen, as I mentioned, two kinds of randomized strategies. When we talked about hashing, we looked at a strategy where, so let's say there's two kinds, right? So there, generally could be more, but let's say that, so if we look at a randomized algorithm, there are two kinds of algorithms you can think of. One is where the algorithm is correct and the resources used, so this could be a resource like space or time, are on average good. Right, so let's say the expected amount of space for your hash table is linear, or the expected running time of your algorithm is n log n, and so on and so forth. And remember, this expectation is taken not over the input data, but over the choices the algorithm makes. So it's worst case for an input, but the expectation is over the choices of the algorithm. That means if you take the same data and run the algorithm a gazillion times, and take the average of all the resource consumptions it uses, that will be the number you get. Okay, for the same thing. Okay. And this is true for any data. This algorithm, this kind of algorithm has a name to it. And historically, the names that were given were names of, well, casino towns. So this kind of algorithm is usually called the Las Vegas algorithm. Sadly, we do not have a Wendover algorithm, so don't get your hopes up. I'm not sure why, frankly. It's just, it just happens to be called Las Vegas. In other words, the algorithm is always correct, but the resources it uses are a random variable that has an expectation. Okay? But then the other kind of algorithm we talked about when we talked about min cuts was an algorithm where, the resources used are fixed. We analyze them. Worst case, it takes n squared time, or n cubed time, or n squared log cubed n time, or n to the fourth time. No expectation here. That's what it takes. The algorithm runs and it stops. Okay? But correctness is probabilistic. So the algorithm is not always correct. But you can prove that it's correct almost all the time. So if you ran it, 100 times, it will be correct 99 times. Or if you ran it 1,000 times, it will be correct 99 times. And you can control it. You can say, I want this much correctness, and you can make sure you do it. This kind of algorithm, it's not a Reno algorithm. It's not in Atlantic City. It's way cooler. It's a Monte Carlo. And you may have heard of Monte Carlo Markov chains, MCMC. Any of you heard of these things? A little bit? Same Monte Carlo. Same intention. Okay? And for different problems, you could ask, what kind of thing do I need? And it's fair to ask, when you need what. If you ever study complexity theory, you will understand that these problems, these kinds of solutions fall into different classes. Problems that are amenable to a Las Vegas algorithm fall into a certain complexity class. Problems that are amenable to a Monte Carlo algorithm fall into a slightly different complexity class. Slightly different in the sense that we're not quite sure if they're the same, but they seem a little different, but we don't know what proof it is. And you could ask, if I have one, can I get the other? Maybe I'm in a situation where correctness is really important to me. Okay? I'm okay with some time, but the correctness is really important. So I really want Las Vegas algorithm, but all I can come up with is a Monte Carlo. Or vice versa. You have some situation where you have a budgeted time, your thing is going to time out after a while, you have to make it stop in a certain time and you really tolerate some error. Okay, but all I have is an algorithm that is guaranteed to be correct. Can I convert one to the other? Question?
Yeah. So here, when we are talking about expectation of the amount of resources, is it over the algorithm, or the set of algorithms, the expectation?
In which case?
In the first case, last case. I mean, the expectation of the amount of resources is over what? Over.
You tell me. You tell me. What is it over? For a randomized algorithm, when we take expectations, what is it over? What kinds of randomness are we looking at? Anyone?
Different trials.
Different?
Trials.
Trials of what?
Trials of running the algorithm from
Why would running the algorithm 2 times make a difference?
because one trial might have, I might not.
No. What is it about the algorithm that changes between trials?
Randomness.
What randomness? Where is it coming from?
So probably coins. Or I mean probably
Coins. We're not. This is not the seminar. Don't confuse public and private. Let's not get into that. So there are coins. Remember, the algorithm as a resource has time and space, but it also has coins, and it tosses these coins. And after a while, its thumb hurts, so it doesn't want to toss too many of them. Okay. So you're measuring in terms of that. Your expectation is over the number of coin tosses of the algorithm. Okay. That's what the expectation means. That's what the probability means in the second part. When you're saying the correctness is with some probability, the probability is with respect to the coin tosses made by the algorithm. Okay? That makes sense? This is a very, very important point. Mainly because the natural or quote-unquote natural way to think about probability with an algorithm is over the data. And if you do machine learning, you will almost always be thinking of randomness over the data. But the data is drawn from the distribution. And I know I've said this over and over again, but I think it bears repeating. In our algorithms, we are still worst case with respect to the input, but we are doing averages with respect to what the algorithm is. Okay? Yes.
So in some sense, for the first one, we are saying we'll eventually get to the right solution, but we don't know on how much time we'll take.
Exactly.
And the second one, we are saying we'll get to the solution, but we don't know how accurate it is.
Or rather, we'll always stop.
We'll always stop, but we don't know how correct its solution is.
Right. And in fact, this is an interesting way of thinking about this, right? So let's say you're searching for something in a space. Right? You're searching for a needle in a haystack, or a virtual needle in a virtual haystack. You could say, I will search till I find it. That's the first kind of algorithm, because you don't know how long it will take. You can say, I will search for 2 hours. That's the second kind of algorithm. You may or may not find it after 2 hours, and that's a chance you'll have to take. Or you can keep going on. And this starts telling us something, right? When can I convert a Monte Carlo algorithm to a Las Vegas algorithm?
You don't fix the result.
Well, my algorithm runs for a certain time and stops, right? It always stops.
I keep running it again and again until I find it.
So one proposal here is I keep running the algorithm. So I run the algorithm and it stops. And I have to decide whether I should run it again. How do I decide that? How do I decide whether I should run it again? What do I need to know?
If your solution is right.
Being right.
Well, I will check if I was right or not. How do I check if I'm right? Let's consider last lecture's algorithm. We want to solve min cut, so we do some randomization. We pick edges at random, contract, and get a number. So I ran this algorithm. My min cut was 5. Do I run it again?
Yeah. First time you keep running until you are making.
Okay, the first time I ran it, I got 5. The next time I ran it, I got 6. The next time I ran it, I got 5. And I got 6. Then I got 7. Then I got 4. Then I got 5. Then I got 6. Okay, when do I stop?
Depends on your input size.
No.
So basically,
You got to tell me a rule. I need a rule. When do I stop?
there is a convergence or something.
When there's a convergence, do I expect to converge? Did I prove anything about convergence? I'm telling you, my numbers are 4, 5, 6, 7, 4, 5, 6, 7, 4, 5, 6, 7. This is what I'm getting. When do I stop?
All these results are acceptable.
Sorry?
All these results are acceptable.
They're acceptable. Are they correct?
Approximately.
But are they correct? Are they approximately correct? Suppose the right answer is 1. They're not even close. Yes?
I think to run a verifier algorithm, that's going to be less expensive than finding a solution.
So what do you mean by that?
It gave you a result that you think is a possible solution. So you could try and find all cuts of size 4 and there's a finite number of those. And
Check and see.
yeah.
While that particular algorithm I'm not sure will work, but your idea is correct. What you need is a verifier. If I had a verifier that says, yeah, the solution is correct, or no, it's not, then I can know when to run it again. That's not always available.
Yeah.
You can't always convert a Monte Carlo algorithm into a Las Vegas algorithm unless you have a verifier. Because then what you do is run the Monte Carlo algorithm, it stops, gives you an answer, run the verifier, verifier says no, run it again, keep doing it.
In this case, you could have used the verifier to go with 1, 2, 3 and see which is the answer.
The verifier merely takes a claimed answer and checks if it's correct. That's all it does.
Yeah, I would.
It can't produce an answer. It's a verifier.
I would randomly pick an answer and verify it.
What do you mean randomly pick an answer? Where randomly answer? You use your point process carefully. Where is this randomness coming from?
I would go with 1, which is the minimum cut.
Where's the minimum cut?
No,
you just ran your Monte Carlo to give you an answer.
Yes, I am assuming I know the answer and it is.
How do you get the answer? You're supposed to find the answer.
I am going from 0 to maximum degree and then picking 1.
How will you find? Suppose, okay, so you want to try all possible answers, right? Suppose your randomized algorithm gives you the answer. Suppose your vertex set is from 0, has 10 vertices, or 10 edges. So your min cut size could be anywhere between 0 and 10.
Yes.
And you run your Monte Carlo algorithm, it gives you 9, 9, 8, 9, 9, 8, 8, 9, 9, 8. How are you going to check 7?
Yeah, but if I don't do the Monte Carlo, like I don't do the algorithm at all, and then I take from 1 to, I know the answer is between 0 and 10, right?
Okay.
I pick 0, 1, 2, 3, 4, 5, 6.
So suppose you pick 5.
Yeah.
I know the answer. What are you going to do now?
And if it's wrong, I go.
No, but how do you know if 5 is the wrong answer?
I use the verifier. Right?
The verifier takes a particular cut and checks if it's a valid.
Particular cut. Okay, sorry.
There are an exponential number of cuts of any given size. You can't try them all. That's what I'm trying to say. The verifier's only job is to take a projected solution and tell you if it's correct or not. Given that, you can then convert Monte Carlo to randomized. But how long will it take? How do you know? You're supposed to analyze. I'm supposed to tell you how long, how many resources I'm going to use. How do I know how long it's going to take to get that answer? So you said, okay, if it fails, run it again. Okay, how many times do you have to run it?
You already have the expectations, right? You will.
No, all I know is I have an algorithm that succeeds with probability P. How many times must I run it? So if I run this process, I say keep running it till I get the correct answer based on what the verifier tells me. How long would I run it for?
Isn't this halting problem?
Is this the halting problem? Is it?
No, you only know with the probability.
Let me change the question completely. Forget randomization, forget algorithms. I have a coin. I'm going to toss it till I get a head. In expectation, how many times will I toss this coin? If I actually had money. Coin. Heads. I'm going to toss it. I got the heads in one trial. That's no good. Let's try it again. Tails. Trial number 1. Tails. Trial number 2. Are you counting? 2. Tails again. Tails again. 4 trails. Someone should come with me to Las Vegas. I'm not kidding. Tails again. Heads. 6, 5. Okay. What's the average?
2.
Why?
I just remember a formula.
Sorry?
I just remember a formula.
What formula?
So for a geometric.
Okay, now you're throwing in words I've never heard before.
So you say, okay, either take 1 toss, probability half, or 2 tosses, probability quarter.
Okay, good. Let's hold that thought. What we're saying is this. So let's say I have an algorithm that succeeds with probability P. I want to find the expected number of times to run the algorithm till it succeeds. And I know when to stop because I have a verifier. Tell me when to stop. Okay. To compute the expectation of a random variable, you take the value of the random variable times the probability of it happening. What is the probability that it stops in one trial? What is the probability that it succeeds on the first try? Half P. So with probability P, it succeeds in one trial. What is the probability that it succeeds in exactly 2 trials? Not one, not exactly 2. It has to fail in the first trial, and then has to succeed in the second trial. Right? And this is the third trial. All the way to infinity. This is basically sum of P times the sum of P to the
1 minus P to the power.
Oh, did I get this wrong?
Oh, yeah, it's there's no I. There's no I in there. There's no I.
What?
Into I, you have into I.
I have to have it. It's an expectation.
Yeah. Oh, expectation.
Okay. Now this is some basic skullduggery from a discrete math class you have to do. And if you know how to do it, there's a little magic trick. If you don't know how to do it, you'll say, how do you come this trick? You know, there's a way to solve these references. And the solution to this is going to be something like, if I recall correctly, if I'm not mistaken. Basically, this series is the derivative of another series which is similar to substitution situations. It's tedious and boring. But what this means is that, going back to our heads and tails example, right? Since success for the heads and tails is finding a head, that success happens with probability half. The expected number of trials to get to a head is 2. So if we go back to our Monte Carlo algorithm, right? If the algorithm, so let's say that our algorithm, it runs in time t of n, it succeeds with probability p, and the verifier takes time b of n. Okay? So how much time is it going to take in expectation to get a correct answer in a Las Vegas mode? So the Las Vegas algorithm, which basically says run this and verify this till you get the correct answer, based on this analysis right here of heads and tails, it's going to say it was run in time. The expected running time of A. Right? Because you run it that many times, and each time you run it and then verify it. So given a Monte Carlo algorithm with a certain success probability, given a verifier, I can construct a Las Vegas algorithm using a basic fact about what is called a geometric distribution. Expected that kind of distribution is called a geometric distribution. The distribution of the number of trials till something happens. When you do independent trials. So notice that in order to solve this problem about how to convert one kind of algorithm to the other, we're really just reasoning about heads and tails and probability. And that's going to be the theme for what we continue on the rest of the lecture. Okay. Any questions about this? Let us go down 2 tailwinds. So we saw that, for example, hashing. Oh yeah, your question.
Good question on Las Vegas.
Yeah.
In the way you define Las Vegas is it's deterministic end, right? But here you are giving a probabilistic expectation of.
No, Las Vegas algorithm is always correct, but its resource usage is a random variable.
Oh.
This algorithm is guaranteed to be correct because it doesn't stop till it gets correct answer. So it will always just keep running till it gets correct answer.
And it has implications. Okay.
So you can go from Monte Carlo. To go from Las Vegas to Monte Carlo is an interesting question, and we'll get to that in a second. Okay, there is a way to do it. It's a little bit easier, in fact. Okay. We talked about hashing, and we talked about the expected value, the expected load size of the distribution. And that's all very well, right? Expectations are great. On average, good things happen. But as we know, good things happening on average doesn't mean good things happen a lot of time. Good things happen on average means, well, on average. The actual average event itself could be something of very low probability, right? And then the things could be happening all around it, but on average, things work out. So, what I'm trying to say is that if you look at the behavior of any algorithm, of a randomized algorithm, and its resource usage or time or whatever, it really is a distribution. And the expectation is only one way to talk about this distribution. It's just one particular number you can extract from a distribution. And it's not always even the most interesting one. For example, suppose I have two algorithms and I'm plotting their running time. Okay, this is the running time. So these are two algorithms. This is the let's see, with number of trials. So as well, not number of trials. Sorry. I want to see how to plot. Yeah, just say trial ID. Okay, and I just sort them. So I'm looking at the histogram of this thing. And here is the resource. And again, I'm being deliberately vague. It could be time, space, whatever. So let's say that's one algorithm that uses resources. The resource usage varies. It varies. It looks something like this. So its resource usage varies between, I didn't draw this right. Let me actually draw a histogram instead of doing all this silly stuff. So in other words, my y-axis will be the number of times I see that resource usage. So number of times I see that resource usage. And the x-axis is the usage itself. So one algorithm, you see usage spanning a wide range of values. So it looks something like this. So it usually goes from some large value here up to some small value here. And on any run, it could be any of these things. And let's say there's a different algorithm whose resource usage looks something like this. It has the same min and max, but it looks something like this. Okay? Which algorithm might you prefer to use? By design, they have the exact same expectation. But which one might you prefer to use? Again, this is the histogram. So you're looking at the y-axis is the number of times you'll see that amount of resource usage. So what we're thinking about is the algorithm marked in red has a resource usage that's almost always in that middle band, and very rarely will sort of go to the sides. And the other one is across the board. So in some sense, the red one, right, which is clearly the answer I'm trying to get you to answer, is the one that seems almost deterministic, right? A deterministic algorithm would have, apart from vagaries of the input, remember this is for a single input, I'm just running it, would be a single spike, just doing one thing. The red algorithm is almost getting there. It's not quite there, but it's getting there. The black one is, I don't know, today if I run it, it will take 5 hours, tomorrow it might take 1 minute, who knows? So you would like an algorithm that runs like the red one, because it's almost deterministic, but measuring the expectation is not going to tell you the difference between them. If I say that I compare their expected resource usage, they will look the same. There is no way for me to tell that the second one is much better. Right? In other words, you need much more information about the distribution of behavior of the algorithm than just the average. You need higher limits, you need variables. And one thing we like to try to understand is the tail. So what is the tail of a distribution? The tail of a distribution, let's say the upper tail. We'd like to know what is the probability that the algorithm will take, more than double the average value. or something like that, or more than something. So we might say, okay, this is some kind of threshold. This is my average, but I really don't want to spend more time on this. How often will this happen? Well, for the red algorithm, this is the area under this curve here, is how many times, how often that will happen, which in this case seems not very often. For the other algorithm, it would be this entire section here, which is to say a bit more often. So they are different, but you have to ask the right question. And so what we like to do with tailbone analysis is to say not so much what is the average behavior of the algorithm, but what is the probability that it exceeds the average by some amount. Okay. Yes?
Can we kind of compute actually, give a formula for the PDF of the behavior of the algorithm?
If you could, then you're right. From the PDF, I can read off these numbers and calculate.
Yeah, my question is, can we compute that PDF, give a formula for that PDF, for example, based on the algorithm that I designed, is the formula for the PDF of the behavior of the algorithm? That's
right. And what I'm trying to say is that if you could, that's great, but in general, you can't. It's very hard. When I say you can't, I don't mean it's formally not possible. I mean it's very, very difficult. It would take a lot of work. And one thing that algorithms folks are, we're lazy. We're lazy as hell. We don't want to do extra work. So what I'm going to show you is ways to figure out these things without computing the PDF. Okay, that's the point. We would ideally like to compute the PDF. It's very difficult to do that.
So
for most algorithms.
NP complete or something like that? Or?
It depends. NP completeness is not the right term for this. There are other complexity measures that capture this kind of problem. And sometimes I don't even know how hard it is. It's just very, very hard. It just seems very difficult to understand what's going on. But I can do simple things like analyzing the table. And the kinds of tricks I'm going to tell you about now are ways to do it. Okay? So do you understand the goal here? The goal here is to understand not just the average behavior of an algorithm, but to understand this extreme behavior. And try to put numbers and quantify how well or how badly it does in those extreme cases. And that's why these are called tailbones, because you're trying to understand the behavior of the table. Okay? Yes? Okay. The first tailbone we will see. And there are 3 bounds. And they're all named after different Russian mathematicians. So the first bound we're going to see, which is a very simple bound, is called the Markov inequality. Okay. And just to remember, we're going to be expressing our bounds in the following form. We're going to say we have some random variable x, and we want to know what is the probability that x is more than something. That's a table. You can also ask for x less than something, which is the reverse table, and that's oftentimes we do. So the Markov inequality, let me write down here now, is going to say this. Suppose x, a random variable, is non-negative. So this is always the same. Okay, this is very important. Then the probability that x is more than some number a is less than or equal to, and I might have to be a bit careless with this. So this is an example of a tailbone. The probability that x is more than some number is less than or equal to the mean divided by the number. And another way to say this, which is equivalent, but is a bit easier to see, is that the probability that x is more than some scale factor times the mean is equivalent. You just substitute a is equal to lambda expected value x negative. Right, the same thing. So in words, the probability that a random variable that's non-negative is more than twice its average value is less than half. And that's kind of what you want to say. Right? So, okay, we know what the average is. What's the likelihood of being very far away from the average? And this is the answer. Yes?
This is for every random variable?
For any, suppose x is any non-negative random variable.
No matter what's the distribution.
the beauty. You see what I mean? I don't need to know the PDF. This is true for any non-negative random variable. That's the power of this inequality. Also its weakness, but we'll look at that.
In this case, can you give this example?
Yes, I will. Let's look at, I'm going to do a simple example that will walk through and give stronger and stronger bounds. Let's say I'm tossing heads and tails, and I want to know if my coin is biased. So I could say, okay, I'm going to toss this coin 1,000 times. I expect to get 500 heads or 500 tails. Suppose I get 501. Should I declare this coin as biased? Should I? What do you think? No, probably not. 502? 600? 700? Suppose I get 800 heads. Is this coin biased? Maybe, right? We want to be able to say these things more precisely. What does the Markov inequality tell us? If I say my random variable is the number of heads I will see if I toss a coin, 1,000 times. Right? The expected value number of heads is 500. So what is this inequality telling me? Suppose I substitute lambda equal to 2. It's saying that if I toss a coin 1,000 times, the probability of seeing more than 1,000 heads is about half. Yeah, I thought that was funny because I only tossed the coin 1,000 times. It's a very weak inequality, but that's what it's saying to you, right? If you just put the numbers in. Does it make sense? I mean, if you just substitute the numbers, EX is 500, lambda is 2, so the probability of seeing more than 1,000 heads is less than half. Clearly, we can do better than that. We know it's 0. You can't see more than 1,000 heads if you toss 1,000 times. But that's what the Markov inequality gives you. Think about it for a second. I want to check something. So let me say this another way now. So let's say, let's do this more formally, right? So I'm going to toss n times and let xi equal to ith toss is heads. Okay? And let x equal to sum of xi. We've seen this kind of trick before, right? Define random variables for each small event and then define your global object as a sum of these things. The expected value of x is the expected number of heads, which is the expected sum of the xi's. Let's say the coin is in fact unbiased. So the probability of any particular coin toss being heads is half. So the expected number of heads is going to be n over 2. Right? 1,000 coin toss is 500 heads. Okay? So now we can say, so the expected value of x is equal to n over 2. Okay? And so we can now say that the probability that we see 750 heads by applying Markov inequality is less than equal to n over 2 divided by 3n over 4, which is equal to so again, what this is saying is that I may have something wrong on it, but anyway, if I toss a coin 1,000 times, let me figure out how many times I'll see more than 750 heads. I should, and I tabulate this thing. So I toss a coin 1,000 times, make a mark if I've seen 750 heads. Toss a coin 1,000 times, make a mark if I've seen 750 heads. Keep my thumb in ice for a while. Toss a coin 1,000 times. Again, write down the lose a number of times. The number of times I should see 750 heads or more is 2/3. At most 2/3 of the time. I shouldn't see it more than that. If I start seeing it all the time, then I can start getting suspicious that maybe this coin is biased. Because the coin that's unbiased, I should not see this more often. So you see how I'm applying this here? I have a coin, I know I have the expected value, This random variable is always positive. And one way to get some intuition for why this should be true, this inequality, is think of it this way, right? If I tell you that the average, suppose we're scoring people on an assignment, and the average score is 80, and the minimum score is 0, so it's positive. Can more than half the class have got a score of 160? Think about this way. Suppose more than half the class got a score of above 160. Then half the class times 160 is 80 already, just for those people. And that's more than 80. All the other people, even if they got a 0, can't bring the average back down to 80. There's just too much there. That's the intuition behind what the Markov equation. If your random variable is not negative, so that you can't pull things backwards too much, you can't also go too far forward. That's what the non-negativity is important. And that's all you need to know about the random variable. We're not using any other property of it. That's what makes it so powerful. We don't need to know the true PDF. It could be a flat distribution. It could be wavy. It could be G. I don't care. If it's not negative, this is true. And this tells me now how to look at my heads and tails. And again, heads and tails is a proxy for understanding how an algorithm works. Any questions? Before I move on to the next step, next kind of inequality?
So in terms of this, it's assuming that my probability function is a straight PDF. And
no, it's assuming nothing.
No, the bound it's giving is saying that half of the values.
That's the worst case scenario. That's why you can't improve the Markov inequality. It's tight. That's exactly an example that shows that you can't do any better than this estimate. I can't get an estimate of better than this expected value of x divided by e. It's a weak estimate because of this property.
It's a very weak estimate.
It's a very weak estimate because I'm assuming nothing about the data, about the random variable.
Okay.
So I see, yes.
So how do you pick, a good value for that? Obviously, if we picked 1,000, that would be, a bad value.
What is it mean by good?
Well, I mean, so you're saying, let's see, 750 heads, right? I mean, how do you know how strong your estimate is, I guess? Or how
I just proved it.
Well, right, you just proved it. But, I mean, in the case of 1,000, we would probably never see 1,000. We could toss it. We wouldn't really gain any information about our coin, right? Because we probably wouldn't see 1,000, so we'd never go over 1,000.
Well, I'm giving you a test right here. I'm saying,
right,
toss your coin 1,000 times
right,
and see if you saw 750 of them.
Right. So how do you know what a good test is? How do you know 750 is a good test?
Because it's giving me that probability of 2/3. It depends on how much it depends on what kind of probability of error I want. And but then, as you'll see, these bounds will get stronger and stronger in a minute. But this gets around how do you design a good experiment, and you'll see. Yeah. Okay. So this is a very basic inequality that assumes nothing about your data. Let's try to add in a bit more knowledge about my distribution and see if we can do better. Because that seems reasonable, right? If I know more about my distribution, I should be able to do better. So then here's the next thing I'm going to do. So the next inequality, after the second Russian, who was actually the advisor of the first one, is called Chebyshev inequality. Or Chebyshev. Or this is an anglicization of the original Russian, so if the spelling is not, you should take this too seriously. The Markov inequality says if all I know about my random variable is that it's non-negative, then that's all I can say about it, and you can't do any better. Chebyshev's inequality says, well, suppose I know something more. Suppose I have a random variable x, again as before, and not only does it have an expected value, it has a variance. It has bounded variance. So it doesn't deviate too far from its mean. So the variance is bounded. Okay? Then in fact you can say more. And here's what you can say. That let me make sure I get this right. Otherwise things will be bad. Okay. This is Chebyshev's inequality. It says, if I have a random variable as before, which doesn't necessarily need to be non-negative, but has bounded variance, okay, then this property holds. So first of all, let me point out that the assumption of non-negativity in my previous example with the Markov inequality did not imply the variance was bounded. For example, my random variable could be, any integer. This is a very badly behaved distribution. There's no variance because it could grow off to infinity with some non-zero probability. And you can design even more things that go off to 0 and infinity but still have unbounded variance. These are called these so-called heavy table distributions. In this case, I'm saying, no, my variance is also bounded. And hopefully you remember what the variance of a distribution is. Basically, it's a difference, the average difference to the mean squared. Right? So also you can think of it as the expected value of x squared minus the expected value of x whole squared. So Chebyshev says you can do a bit better. And it may not be obvious to you why this is better in any sense, but I want to bring your attention to this fact that this is an a squared now, not an a. And what this essentially is saying is that, and I said this correctly. Yeah. What this essentially is saying is something you may have seen. So you've heard of, for example, maybe if you've heard of like a 1 sigma test and a 2 sigma test with statistics. And what they're saying is that, for a Gaussian distribution, most of your distribution lies within 3 standard deviations of the mean. You've heard something like that? Or 66% lies within 2 standard deviations of the mean, and so on and so forth. That is this. Or rather, you can think of this as saying the same thing. And to see that, I'm going to rewrite this expression again a little bit. I'm going to measure distance from my mean in units of the variance. Just like we said with the Gaussian, 3 standard deviations, 2 standard deviations. Okay, so I'm going to rewrite this as So let me rewrite this expression as, I'm looking at the probability that x minus e of x is greater than or equal to a times sigma, where sigma is the standard deviation, which is the square root of the variance. Right? And if you put this in now and plug it in, what do you get? In other words, if you measure your distance from the mean in units of the standard deviation, you get this dimensionless quantity, which is the probability of this, which is what we said the Gaussian is 2 sigma, 3 sigma. So A would be 1 or 2 or 3, and you get these bounds. Okay? So does the statement of the lemma make sense? The theorem of inequality? We're going to apply it now to our canonical example, but does this make sense to say this? So again, I'm using the variance, which is bounded, and I'm getting a bound which I'm hoping or claiming is strong. Okay. All right.
Square root of variance.
Yeah, sigma is the standard deviation. So that makes sense. The variance is this. Okay. All right. So let's try to apply it to our problem. And remember, our problem was we're tossing a coin n times, and we're looking at the expected number of heads, and the probability of the number of heads deviating by a certain amount. Okay. Okay. So again, once again, we had x was equal to sum of xi. I know that the expected value of x is equal to n over 2. But what is the variance of x? This is a little bit harder now. I have to do this complicated calculation. Remember that the variance of a sum of random variables is not the sum of the variances, unless the random variables are independent. If the random variables are independent, then in some sense they don't affect each other intuitively, so the variances don't matter. In this case, my coin tosses, hopefully my coin does not know that I just tossed it. So I will assume that each coin toss is independent of what came before. Okay, it's not affected by what came before. I have not disturbed the molecules in the air sufficiently to sort of affect the thing. Okay, that's an assumption I'm going to make. Assuming I have independent coin tosses, then in fact I can say that the variance of x is equal to the sum of the variance of the xi if xi are independent. Okay, but what's the variance of a single xi? So the variance of xi is equal to the expected value of xi squared minus the expected value of xi whole squared. Yes? Okay, this expected value of xi is half, because 0 with probability half and 1 with probability half. So this is going to be 1/4 here. What is this? Expected value of xi squared. Well, xi squared is the same as xi. It's a 0 and random variable. So that's just the mean, which is half. So the variance of x is equal to, okay? All right. So now I want to say, okay, now I want to apply this to my problem. And my problem, if you recall from before, was what is the probability that x is greater than 3n over 4? Okay? And now I want to say, okay, well, all I have from the Chebyshev inequality is this expression here. So I have to get the thing I want to evaluate in that form, right? So I'm going to do this. I'm going to look at, first of all, I'm going to look at not just the probability that x is more than 3n over 4. I'm going to look at the probability that x is, okay, so I'm going to write it this way. What is the probability that x minus n over 2, which is the mean, is greater than n over 4? So I'm overcounting. I'm looking at the probability not just that it's more than 3n over 4, but that it's less than 1 over 4. So this probability will only be bigger, so it's fine. If I can get up to one of this probability, I'll end up to one of the previous probability as well. But now this is in a better form because it's in the form of what I want. So now if I look at this expression, I know that this is x, this is my mean of x, and this is my a, right? I think this is what I call a. Yeah. Yeah. Okay. So then I can apply this argument and say this probability is less than var x, which is n over 4 divided by n squared, a squared, which is n over 4 whole squared. And so this probability overall is less than 4 over n. And I want to compare this to what I got from the Markov inequality, which I will write here, which was actually just so what has happened here? I have looked at the same algorithm, cost points and count the number of hits, but I have used a different analysis technique. And somehow I'm getting a much better answer. Because 4 over n is a really small probability. 2/3 is a big probability. The probability, now I'm saying, no. In fact, the probability of seeing more than 750 heads is really 4 over n. It's much better. Because the n is larger, I'm really not going to see this happen. What has happened here? Why have I suddenly been able to prove a better bound? I am using more information about the random variable. So this goes back to this question you had about, can I build a PDF for the algorithm? I can't in general, but I can make observations about what the algorithm is doing. And the stronger observations I can make, the better the bound I can show for the same algorithm. Which is why randomization is often a lot of work is in the analysis. You just do better and better analysis and you get, and the algorithm just works. The algorithm like, yeah, whatever, I'm just going to do my own thing. Okay? And so this is where the independence assumptions help us. And independence is a very powerful tool. Independence allows us to sort of coalesce things. Many of you heard of the central limit theorem? Right? The fact that, if you take an average of a bunch of Bernoullis and in the limit it looks like a Gaussian. We're going to see a version of that right now in a second. But that's the idea, that if you take a bunch of independent things and average them, things concentrate. You don't really end up deviating from the mean that much. That's what this is telling you. The more number of trials I have, the less likely it will be that I'll go above 3 and over 4. That I'll go above 75%. That's the average is half. Is 50%. The proof of the Chebyshev inequality is actually very simple. It just uses the Markov inequality. It defines an auxiliary random variable, applies a Markov inequality to that, and then declares it. The proof's unknowns. It's very clear. Any questions? Okay. Yes?
Can n be 0?
Can n be 0? Sure, but then what are you saying? You're saying I toss a unbiased coin 0 times, and I want to know what the probability is that I will see more than 0 heads. You get nonsensical answers. So it doesn't make sense to talk about n equals 0. But remember, this is not, the answer you get here is what? The probability is less than infinity. That's not wrong, it's just useless. Because all probabilities are less than 1. So just saying this less than infinity, basically saying, I have no clue what's going to happen. Which is fair, because I haven't tossed a coin yet. So there's nothing, you don't get a wrong answer here. You just get an answer that has no value.
And also in the previous
yeah,
you're not including the A, in the previous equation.
Which one? This one?
Yeah, it's greater than A, or it is greater than or equal to A.
Yeah, I'm being a little sloppy here.
In Markov, it is non-negative, so you are including a 0.
I'm not sure I follow.
Okay, anyways, I'm just asking.
So yeah, I should say I tend to be very bad at making sure these things. If this makes you happier, you can do it. These things don't matter. In the limit, they're all continuous. It doesn't really matter whether any mathematicians in the audience are now cringing. Like, no, but okay. But I apologize. But yeah, don't worry about those particular. Okay, we'll take a very, very short break, like a minute and a half. And then we'll get back to this. Actually, well, better to talk. Let's go. There's 8. So expect that everybody like right. That's because of how you do the Chebyshev. So Chebyshev one is like Chebyshev. You're measuring the here, the Markov inequality is the one set. Yeah, because you're talking about one set. You only measure one set. The trick with Chebyshev is you run auxiliary and that's right. Exactly. So yes. Just give you a stronger one. Saying the probability of being in either of these places is less than. So in fact, I would say it's half. You have to do a different analysis to see what is. Yeah, you how much profit. You can do a Bayesian analysis. You can do all that. Okay. Let us continue. All good things come in threes. So now we're going to have a third bomb, which is the big granddaddy of all these bombs. Also named after a Russian, who I think was either the advisor or the student of one of these. So this bound is called, sometimes it's called Chernoff bound. Sometimes it's called a Chernoff-Hafting bound, depending on the version you use it. Sometimes it's called Bernstein's inequality, and it goes on. There's a whole book of families of these bounds. It's actually, what I'm going to tell you is one example of an entire class of bounds, which are very, very strong. But once again, the idea is that if I knew more about the distribution of my random variable, I might be able to say more about all the variables. And as always, we're looking at the table. Now, before we go on to the Chernoff, I want to point out one thing. In fact, let me just write it here. So it helps to kind of squint at these things a little bit. So for Markov, we had some probability of x being something more than some constant, let's say a times the mean, and this was less than 1 over a. For Chebyshev, we had some probability that the difference from the mean was more than some a times the standard deviation, and that was 1 over a squared. squared. This is not accidental. You're using the second moment of the distribution for a Chebyshev inequality, using the variance. And that in some sense is why you can prove a bound that now depends inversely quadratically on this distance parameter A. For the Markov inequality, using first order properties of the distribution, the mean. So the bound you get depends kind of linearly in 1 over t. As you use higher and higher moments of your distribution, which may not exist all the time, but if you know they exist, that's good. You get better and better tail bounds. Things you can start saying sharper and sharper things about how things concentrate. And of course, the limit of this is saying, let's look at all the moments of the distribution, all the way up to infinity. What kind of bound do you get there? And you can't always do that, right? Not all, some distributions admit a variance but no third moment. Some distributions admit finite moments but nothing more than that. If you're lucky enough to live with have a distribution where all moments exist, for example, the Bernoulli distribution that we talked about, or the binomial, then you can go much further. And that's what the Chernoff bound is going to give you. It's going to give you a way to reason about all the moments of the distribution simultaneously. The proof is a little bit complicated, and I don't like to do it on the board. I did it once, and it was just so annoying and painful that I never do it again. It's in the notes though. The trick is to use something called the moment generating function. There is a function that generates all the moments of distribution. It has a very nice, it's a beautiful, beautiful function. It has very nice properties. You can characterize a distribution by all its moments by this moment generating function. In the sense that if two MGFs are the same, then the distribution are the same. Up to probability, up to a measure zero subset. But that's how the proof works. But I want to at least state the result itself. And then we can understand how it works. So a Chernoff bound or a Chernoff-Houghton bound, depending on which sort of space of which domain of your random variable is, looks something like this. And again, I want to make sure I get the statement right so I don't mess up. Okay. So we're going to set up a very general statement. Okay. So again, I'm going to have a bunch of random variables, and they're going to be very general. So let's say I have x1 through xn. Each random variable is a Bernoulli. So each xi belongs to set 0, 1. So these are what I call Poisson trials, just to be confusing. And let's say that the probability that xi is equal to 1 is pi. It's not even the same for each distribution. It could be different. Okay, which is also equal to the expected value of xi, of course. And let's say x is equal to the sum of all the xi, and let's say mu, which is equal to e of x, which of course is equal to the expected, it's the sum of the expected value of all the xi, which is equal to the sum of the r. Right? All this stuff set up, and assume that these distributions are such that since they're Poisson, all moments exist. As before, I want to give some bound of the form, what is the probability that x is more than something, right? What's the table? Okay. So let me give you a couple of simple versions of this bound. Okay, and then probably the one that's going to be the most useful will look something like this. So fix delta less than equal to 1. So that, okay, some parameter delta. This is going to measure our distance. The probability that x, okay, is more than 1 plus delta times the mean. So if you think of delta as less than equal to 1, think of it as 1. So the probability of being more than twice the mean, right, if you want, is less than equal to, and again I want you to look at the 1 over a and the 1 over a squared. I want you to see what happens now. This is going to be e to the minus mu delta squared. This is at least one version of what is called a Chernoff. So again, before we start playing with it, let's try to understand what it's saying. What it's saying is the following. I have some random variable x, and I have this construction 1 plus delta times mu. Think of that as mu plus delta times mu. So what I'm saying is that, you know, if this is my mu here. What is the probability that x is somewhere above this, where this distance is delta times mu? So what's the probability that x is in this range here?
Mu is the mean.
Pardon me?
Mu is the mean.
Mu is the mean. And it's always with respect to mean, right? You have to have this with respect to mean. So what is the likelihood that if my mean is there, I'm really far away from it? Where delta measures the sense of how far away I am. And what this is saying, what something like, you know, Markov or Chebyshev would say would be something like 1 over a squared. This is saying something even stronger. It's e to the minus delta squared. And there's of course a mu term, but let's pretend this one there. So the probability of being that much away from the mean drops off not with 1 over the distance or with 1 over square distance, but exponentially the distance. And this extra power comes from the fact that proof of the Chernoff bound uses all the moments of my distribution and not just the first moment or the second moment or the third moment. You can actually get weaker versions of a Chernoff-like bound by saying if I only have k moments, then I get, you know, I'll get something like 1 over a to the k, roughly speaking.
Where did you put the moments info into this?
The proof of how the Chernoff bound works is to write down the moment generating function of the distribution, which is this complicated object that.
But my question is, where did you take? So for you took the for 1 by a square, you took
the variance. Second moment. Yeah.
And you. And it's dependent on the moment, right? Because you put variance by.
Yes, but it turns out that the moments, if the moments all exist,
if the moment also exists, okay.
that they're finite is enough. That's the power of Chernoff. Because if the moments all exist, the distribution is dropping to 0 very rapidly. Because again, you should think about moments in the following way. Think of this way: the first moment of the distribution is its mean, so the distribution will be varying in average. The second moment controls its variance. If the distribution does not fall off quickly enough as you get larger and larger, then you remember you compute the expected value of x squared. X squared goes up very rapidly. Its probability better drop off quickly, otherwise you're going to get an unbounded value. Now think of x cubed. If x cubed doesn't drop off rapidly, you're going to get an unbounded value. So what we're saying is that if all the moments are finite, then the distribution is dropping off so rapidly that actually doesn't matter what they are. All that matters is the mean.
So, if I have a distribution like this, then would all the moments exist?
I don't know. Depends on what those things were. Any distribution over a bounded support has all moments. It has to go to infinity for this to make any sense. Yes?
So how we are going to know that the algorithm that we designed has a variance or other moment?
Because most of the time the algorithms you're going to describe are going to be algorithms that give a 0, 1 output. They're going to be either correct or not. Remember we said, oh, the algorithm is correct with probability p. That's one of the xi's. And then we're going to run it again independently. We're going to get another instance. In fact, all these p's are going to be the same for the algorithm.
You're doing a binomial calculus.
Exactly. So most of the time, randomized algorithm is going to be a simple binomial example of it. So it's going to be really easy. Because you're going to run independent trials of the algorithm. That's why, remember we did incuts, I said, oh, the probability of success is 1 over n squared. Let's run it n squared times. That, by the way, was an example of what I talked about right now. If something is the probability of success of 1 over n squared, you run it n squared times the expected success rate will be, you definitely get a success. So our randomized algorithms are going to be a lot simpler. Once you get into very advanced material in randomization, then you start playing with these things a lot better. But for the kinds of algorithms you will be encountering, most of the time the algorithm either succeeds or fails. It's a binomial. You can apply the Chernoff bound very simply. You don't have to worry about all these other complicated things. Because we know and we can prove that for binomials, all the moments exist. That's why it's useful to have this bound. This bound is very easy to apply. Run the algorithm 10 times and you can apply Chernoff. Okay? So again, the proof is in the notes, and I will not go over it here. It's actually very interesting. It's a little bit clumsy. But I want to show you what happens now. Let's go back to our nice example. Okay. So we have this example of trying to figure out, what is the likelihood of getting more than 750 heads. I want to apply it here. Okay, so let's look at this example. I'll go to the next page and I'll write this dilemma down again. So we're saying that the probability that x is more than 1 plus delta times mu is okay. So we know that if x equals to sum of xi, then the mu for the coin toss example is equal to n over 2, right? And now we want that 1 plus delta times mu should be equal to 3n over 4, which is what we're trying to do, right? So that means that, I don't know, what is it going to be? 1 plus delta is equal to 3n over 4 divided by n over 2, which is 3 over 2. Okay? So let's just apply the bound now. So we're saying now the bound is going to be minus n over 2 times half times half times half. Yes?
Yeah.
And again, I want to compare this to in fact, let me rewrite this just to make it easy to see. The same question, what is the probability that I'll see more than 750 heads, can be answered in 3 different ways. Each bound getting better and better and better, stronger and stronger and stronger, just by redoing the analysis. This bound is very, very small. It is exponentially unlikely as n increases that you will see more than 750 heads. That was, linear 1 over n. This is exponential. Your tail is dropping off very fast. This Chernoff bound here is one way of thinking about what the center of the material is saying. That is basically you're getting a Gaussian behavior. E to the minus mu delta squared. And so when we have a randomized algorithm, the fact that you can say that this thing happens exponential, the tail is exponential, means a couple of very important things. Since that n shows up in the exponent, right, the number of trials, right, it means that if you ultimately want to get a probability of success, as I've said, which is something like 1 minus 1 over n, or 1 minus 1 over n, 1 over n squared, something that's polynomial in n, the error should be polynomial in 1 over n, you only have to increase the number of trials you do by a log factor. So again, you have to imagine putting in think of n as some number of trials, just putting in log of whatever the true value you want is. Right? That the e to the log of that gives you the exact probability you want. But that's the win you're getting. When you use a strong bound like a Chernoff bound, and you know that the tails drop off exponentially, if you take an algorithm that runs with a certain probability p and just run it logarithmically many times, your probability of success will become very, very large because of a Chernoff bound. If you just did a Markov inequality, you would not be able to say much about it. If you're doing Chebyshev, you'll be able to say a little bit more. But because you can apply a Chernoff bound, you can say that I repeat this logarithmic times. And then by Chernoff bound, my probability of error goes down to something vanishingly small. And that's why randomization in some sense works. You're using the fact that the algorithm can be designed to have some constant probability of error, and then you amplify it using this tree. This is called amplification. And that's why we study these bounds, and that's why there's lots of work. There's whole textbooks on how to analyze these things better. It's because you can, by being careful about how you understand the randomness being used by the algorithm, you can make sure and say, oh, actually, I'm going to run it log n times. I can run it log n times, or even fewer times, or even one time. I think that's enough. That actually improves running time of the algorithm by doing a better analysis. Because the behavior of the algorithm becomes even more deterministic. It drops off in the short. So that's the big picture of why we study K bonds and why they're important and sort of integral part of any study of randomization. How you need to be able to understand at least how to apply these kinds of bonds in order to see how an algorithm is doing. And you know, when I give out some homework questions, I'll try to help have the homework walk you through how you do it. So you sort of slowly get to sort of see how it's going. So you get some practice to it. There's a question. You have a question? Okay. Any other questions? So again, there's a lot of probability. Maybe you're a bit rusty. Might be good to sort of brush up, use some of the material that we handled earlier. But you'll get used to it. All right. See you next week.